In this video, we're having a look at the types of reaction that we should have covered at GCSE, with particular reference to some of the balanced equations and different types of equations that we might come across and should already be familiar with. So what are the different types of reaction? Well, there are lots and lots that you've already covered at GCSE, but I'm only going to go over the most important ones and the ones that really relate to the types of equation we were just talking about. So the first is combustion, very well-known reaction, and it certainly comes up with balanced equations, and they're quite easy to balance if you follow the steps correctly, so we'll go through that. We've got precipitation. This is something that students find quite hard when they're looking at ionic equations, so we'll go through that again. We've got acid-base reactions. These are really common. Obviously, forming salt and water usually. We'll look at how that happens and also look at ionic equations for acid-base reactions. And then redox. Redox because redox reactions are going to include those half equations, those electrons lost, electrons gained. So we'll look at those as well. Displacement is just a specific type of redox reaction. So we'll look at that as well, just the two main examples of displacement that we see at GCSE. There are some others in the organic chemistry that you should know about. So addition reactions, substitution reactions, and condensation reactions. But we're not going to cover this in this video because we're really looking at the non-organic side other than combustion, which we will include, because they're not really equations where you would do a lot of balancing or a lot of different types of reaction like ionic or half equations. Also thermal decomposition. There's two types of thermal decomposition. Cracking, again that's an organic reaction, quite easy to balance, and also decomposition of carbonates. Both of those are easy to balance, so we won't include those in this video. Electrolysis we're also not going to include, even though it does include half equations. That will come under the redox topic. So let's look at combustion. And I'm only looking at complete combustion because it's very unlikely that you'd be asked to write an equation off the top of your head for incomplete combustion. So the general word equation is going to be our fuel, which is usually a hydrocarbon, could contain hydrogen, carbon and oxygen. We'll look at both examples. Reacting completely with oxygen, so there's an excess of oxygen to make carbon dioxide and water. So here's an example, and this one is not balanced because we're going to talk about the balancing now and go through how to balance it. Okay, now I've got a colour for my pen so I can show how to balance it. So, the one thing when we're doing this, so first we've done is just got a symbol equation here. Let's talk about the symbol equation before we talk about the balancing. So we've got a hydrocarbon here with a nice big number of carbons, 11 carbons. It's an alkane, saturated, because it has 24 hydrogens. So 11 times 2 is 22, plus 2 is 24. Okay, and then we've got our oxygen, which remember is O2, because all of our gases, other than the noble gases, are diatomic. And then we're always going to make carbon dioxide and water because this is complete combustion. So let's look at the numbers, and what we're going to do is balance the right hand side first. There's no specific order to balancing equations. If you start with the oxygen, it's going to be too difficult. So I know that all of the carbon goes into carbon dioxide and that each carbon dioxide molecule contains one carbon. So if I have 11 carbons in my hydrocarbon, then I will have 11 carbon dioxide molecules. Following that logic, I've got 24 hydrogens. They all end up in H2O, but it's H2O this time, so there's 2 hydrogens per molecule. So I'm going to need 12 water molecules. So now I can do the oxygen, and remember this is excess oxygen, so you can have as much oxygen as you like, which is why we do it last. So 11 times 2 is 22, plus 12, lots of oxygen there, so that's 34 oxygen atoms, but we have an oxygen molecule that goes around as diatomic, so 34 divided by 2 gives me 17 O2 molecules. So that's so far so straightforward, and one of the reasons that's so straightforward is actually because it is an alkane with an odd number. So for an alkane with an odd number of carbons, that is as far as you would have to go. What about then if we have an alkane with an even number? So we've got butane here, 4 carbons, 2 lots of 4 is 8, plus 2 is 10. So we follow the same steps for the carbon dioxide and water. Then that tells us we're going to need 4 carbon dioxides and we're going to need 5 waters. So the reason this ends up slightly different is if I do 4 times 2 I get 8, then I've only got 5, got an odd number of oxygens in my water molecules. So 8 plus 5 gives me 13, which is an odd number, but oxygen is diatomic. Now there's absolutely no reason that what you can do is simply write 6.5. So 13 divided by 2, 6.5. You can't do that with something like C4H10 or CO2. You can only do that with a symmetrical element, a diatomic element such as O2. So you can have half an O2 because if you cut O2 in half, that is a whole oxygen atom. You're not cutting an atom in half. And really remember the numbers in front refer to moles. You can easily have 6.5 moles of your element. If you don't like that, you can put numbers in front and double everything up. So you could have 2C4H10, you could have 13 instead of my 6.5, and then 8, and then 10. And there's nothing wrong with that, except for 2 reasons. One is you've got to remember to double everything, and so you're more likely to make a mathematical mistake. And the second is that at A level, you are going to have to be able to write equations for the combustion of 1 mole of an organic compound, and therefore you need to be able to get into the habit and get comfortable using those halves in front when you need to. Last combustion example, we're looking at ethanol. So ethanol's got an oxygen in it already, and its structural formula is written a little bit differently. It's not written C2H6O. We normally put the OH at the end because it tells us that it's an alcohol and not some other type of organic reagent with an oxygen in it. So we've just got to be careful of that when we're doing our balancing. So again, we're going to still follow the same steps of doing the carbon dioxide and the water first. So I need 2 carbon dioxides for my 2 carbons. Careful counting your hydrogens. I've got 6 there on the left hand side because it's H5OH. So I'll need 3 lots of H2O. Counting up my oxygens, I've got 3 in the water and 4 in the carbon dioxides. So that's 7, but over on the left hand side I've actually got 1 oxygen in my ethanol already. Take that away, leave 6. 6 divided by 2 gives me 3O2. So that's my combustion equations. Nice and easy, and there's no half equations or ionic equations because this is covalent stuff. The rest of the equations are all going to be to do more with ionic substances.